Okay people, let's continue. Next topic is valence bond theory, something that you people have already done in class 11th, and I know everyone remembers class 11th का valence bond theory. Very good, क्या बात है. Now quickly give me the primary valency over here and secondary valency. Primary valency was also called as oxidation number, and the secondary valency was coordination number. Jaldi jaldi find for me primary valency and let the charge on Fe be X. Water is neutral monodentate. So what's the charge on Fe? Plus 2. So the oxidation number here is 2. And what about coordination number? 6. ठीक है. चलो. Now Fe. Atomic number please. 26. Quickly give me the configuration for Fe. Argon 4s2 3d6. But I'm just writing it like this: 3d6 and 4s2. With me? What will the configuration be for Fe plus 2 then? Argon 3d6 and 4s 0. d6. How will I arrange these electrons? 1, 2, 3, 4, 5 and 6. With me? 4s is now empty. All this is basic. We've already done this. Now, how many ligands do we have here? There's a monodentate, water, and how many aqua? In total are there 6. Coordination number 6. Which means how many lone pair of electrons will be given to the central metal atom? 6. So the central metal atom has to accommodate how many electrons? How many? 12. Or how many lone pairs? 6. Where will it accommodate? In the empty orbitals which are available. Which one do you see empty? 4s can accommodate 2 electrons or 1. But how many more lone pairs are going to come to the? 5. Where do I accommodate them? 3. See, they are going to come in pairs. दोनों को यहाँ पे तो मैं नहीं डाल सकता. Excellent. Fourth shell पूरा empty है ना? So 4s has, for the fourth shell has 4s, 4p and also has 4. How many lone pairs will be accommodated in the third shell? How many left? 2. Where will I accommodate them? D has how many orientations? 5. But out of the 5, how many are we going to use? 2. Did you people get that? So ये जो yellow वाले हैं, where did these electrons come from? Lone pairs from ligand to the central metal atom. Did you people get that? Please respond yes or no. Samjha? It's going to come in pairs. So दोनों आए तो कहाँ पे adjust करूँ? I mean if you people got that. ठीक है. So now, can someone give me the hybridization over here, please? We've used 1s. How many p's have we used? Or d? So what is the hybridization? sp3d2. Give me the geometry. Octahedral. Octahedral is also known as dash, people. Square by pyramidal. Give me the number of unpaired electrons. 1, 2, 3, 4. So can someone give me the magnetic moment? How do you find magnetic moment? Under root of n into n plus 2. N is 4, so that is going to be root 24 Bohr magneton. Yes or no? This is exactly what we did in VBT chemical bonding. Bolo re. Sure. Now we have so let's say this is the first coordination complex. Now, similarly, find for me hybridization, geometry, and magnetic moment for this complex. Yes. So this is the complex. इसे ले लो या K4C6 K4FeCN6 ले लो. Now give me same the oxidation number and Fe over here. Cyano or cyanido is -1. Potassium is group 1 element, so +1. So how much will Fe be? +2. If Fe is +2, what is the electronic configuration? 3d6 4s2. I hope इतना आता है. बोलो रे. What will Fe +2 be? 3d6 4s0. Yes or no? After this, what will we do next? What is the coordination number over here? 6. So how many lone pairs are going to be? We have to form 6 coordinate bonds. So the central metal atom is going to get how many lone pairs? 6. Where will the 6 lone pairs be accommodated? Yes. In short, can I say all this is going to remain the Bolore? Will this change? I repeat, will this change? Bolore, yes or no? No, it won't, right? What will the magnetic moment be? Root 24 Bohr magneton. Same ही आने वाला है. Anyone did not get that? But here's the catch. Hybridization is a theoretical concept that we are saying that the hybridization is sp3d2 geometry octahedral. ये हमने theory बनाई है. But magnetic moment is something which we can determine practically. आप actual practical check कर सकते हैं that the magnetic moment is experimentally determine कर सकते, that is 24, which is as per what we have also got. Theoretically the value is 24. इधर तक समझा? बोलो रे. However, what was observed in the case of potassium ferrocyanide is that the magnetic moment experimentally determined is 0. What are we getting theoretically value? 220. Experimentally, theoretical value, experimental value root 24. So in case of hexa aqua ion, the value experimentally ho ya theoretically ho, the value of magnetic moment was root 24. But hexacyanoferrate के केस में the theoretical value came root 24. But when you try to calculate the same practically, what's the value? 0. When will magnetic moment be 0? When will magnetic moment be 0? I want this value to be 0. Then what should be 0? The number of unpaired electrons should be, in short, we are getting over here that number of unpaired is, how is that possible, number of unpaired? Because we know the number of unpaired here is, for example, ये जो Fe2 plus है, we know that it is 3d6. So how will you write 3d6? Pehle same spin, and then you start pairing it up. Which rule is this? That electrons of a single spin will first fill the orbital and then the pairing takes place. It was Hund's rule. It was Hund's rule. Pauli ne alag bola tha. Pauli said that any electron will have different set of 4 quantum numbers. It was Hund's rule. But what's happening here? If I want the number of unpaired electrons to be 0, 1, 2, 3, 4, 5, 6, the electrons which belong to Fe in the 3D shell, they have to fill like this. But it is not following. यहाँ पे क्या हो रहा है? Disobeying Hund's rule. But we have to do that. Why? Because we're getting the number of unpaired is 0. And how many lone pairs are now going to come in? 6. Where will you first accommodate the first? Where will you accommodate the first 2 lone pairs? In 3D. 1, 2. Next, the third lone pair in 4s. How many done? How many left? Where will you accommodate those? In 4p. Where did these yellow electrons come from? Lone pairs from ligand. ठीक है, short में ही लिख रहा हूँ. Now give me the hybridization. Hybridization is D2 sp3. Now it remains octahedral. अब ये प्रॉब्लम आया कि in case of aqua, in case of hexa aqua ion 2, the magnetic moment experimentally हो या theoretically हो, it was the, But when we were using cyano, hexacyanoferrite, the magnetic moment theoretically कितना मिला था, but experimentally कितना मिल रहा है? This couldn't be explained by VBT. VBT couldn't explain this कि भाई ऐसा हो क्यों रहा है. Why are electrons getting paired against Hund's rule? This couldn't be explained by VBT. In order to understand that, we move ahead with CFT or crystal field theory. Did you people get that till here? समझा? अब ये समझना ज़रूरी है. So, we start with CFT or crystal field theory. Now, before we jump into the theory, how many orientations are there for the D subshell? 5. Can someone give me the 5 orientations of the D subshell? D, X, Y, D, Y, Z, D, X, Z. Very good. D, X square minus Y square and D. Last year in atomic structure we did this. ये triplet को क्या बोलते हैं? Excellent. Anyone else who remembers that? What do you call these three together? एक जन को याद है पूरे क्लास में? बहुत बच्चों को याद है पूरे क्लास में. This will go online. Yes. Very good. क्या बोलते थे इसको? T2G. और इसको क्या बोलते थे इन दोनों को क्या बोलते थे? Please don't say 3G, 4G, 5G. क्या बोलते थे इसको? Excellent, very good. इसको बोलते थे हम EG. There was one more name for this. These are also called as excellent. Shape बना ले पहला. So this is X, Y. Double dumbbell थे ये. Okay, and this will be YZ and XZ, same shape. क्या बोलते थे इनको? Very good. Along the axis orbitals. क्या बोलते थे रे? Along the axis orbitals. These two, anyone remembers the shape? बहुत सारी चीजें इनकी की थी. Do you remember where the nodes were? Where the nodes are for XY? नोडल प्लेन कौन कौन से थे यहाँ पर? XZ and YZ. ठीक है, so on and so forth. तीनों के लिए. How is dx square minus y square? It's like this. And how is dz square, people? This was called as donut shaped, medulla shaped, yes or no? These were together called as, these are in, oh pardon me, these are not along the axis, sorry. These are along the axis. These are in between the axis orbitals. We will remember that. Okay? All the shapes are there. Very very important. सारे NCERT में shapes दिए हैं. पता होने चाहिए shapes. Now, why are we drawing these shapes? Because ligands form dash type of bonds with the central metal atom. Form coordinate bonds. These coordinate bonds are formed with the central metal atom along the axis. इसका मतलब what's happening is, ठीक है, let's say x axis और y axis है, ये आपका ligand है. Ligand wants to form a bond with the central metal atom. The origin is where the metal is. It wants to form a bond with the central metal atom. So the ligand will approach the central metal atom. कहाँ से? Along the axis. I repeat, ligands approach the central metal atom along the axis. Now, along the axis are which orbitals? Ligands approach the central metal atom along the axis and repel the electrons present in which orbital? EG. If you want to still visualize this, imagine this is your central metal atom, and let's say I'm drawing the dx square minus y square wala orbital. This is dx square minus y square. Now when I look at a configuration like d6, this is d6. The first three are T2G. The last two electrons are EG. Which means, let's say एक electron यहाँ पर है, एक electron यहाँ पर है. The thing is actually one of them is present in dx square minus y square. The other is present in dz square. But let's say कि दोनों यहीं पर है. Ligand आ रहा है. What's the charge on the ligand? It's a nucleophile, electron rich. So what charge will it carry? Neutral भी होता है, negative भी होता है. These are approaching, they want to form coordinate bond with the, तो ligand आ रहा है. Electrons negatively charged. यहाँ पे भी क्या है? They are going to what? Repel each other. They start repelling each other, and these electrons jump to T2G. Did you get that? What exactly is happening? I repeat, ligands approach the central metal atom along the axis. When they approach along the axis, they start repelling the electrons which are present in EG. That is, which are present in dx square minus y square and dz square, and these electrons jump to T2G. So what's happening is the d orbital, this is a d orbital. I'll give you all that theory maybe, but it loses its degeneracy. Anyone remembers what was the meaning of degeneracy? हमने किया था in atomic structure. This axis represents potential energy. Degeneracy means all of them have the same energy. So all d orbitals, dx square, dxy, dyz, dxz, dx square minus y square and dz square, all of them have same energy. But when the ligands approach they lose their degeneracy. सबसे पहले the energy of the d orbital increases. And the d orbital splits into two further orbitals. The ऊपर वाला orbital is called as EG, which is d x square minus y square and d z square. The orbital below is T2G, which is dxy, dyz and dxz. This is called as Bari center. The energy of T2G increases by 0.6 times octahedral energy, and the energy of T2G falls by, or is as compared to the Bari center, is 0.4 delta naught, where delta naught stands for octahedral This phenomena is called as, studied this in D block, again समझेंगे in detail what is DD transition. I'm so sorry. So it's not that कि ये increase हो रहा है और ये decrease हो रहा है. See, it is increasing for both T2GB and for EG. But when you look at Bari center, how much is the increase in T2G? Increase in EG as compared to T2G? That is the value that we have written. Getting that? Because electrons jump from EG to T2G. So one of them have to be a lower energy level pe, hence higher stability. So whenever possible, electrons will jump from a higher energy level to a lower energy level, and this phenomena is also called as crystal field splitting energy. इसको हम बोलते हैं CFSE. The crystal field splitting energy is given by number of electrons in EG into 0.6 times delta naught plus number of electrons in T2G into, since it's a drop, minus 0.4 delta naught. The formula becomes CFSE is number of electrons in EG into 0.6 delta naught minus number of electrons in T2G into 0.4 delta naught. With me till here? Bolo re. So let's say I have configuration D5. D5 मतलब so this is the configuration for D5 before pairing. How will D5 look like after pairing? what we just did, so next two electrons there, we just shifted them from EG to T to G. Now tell me, how many electrons do you see here in EG and how many electrons do you see here in T to G? Remember, your first तीन are T to G and these two are EG. So how many electrons do you see in EG? How many electrons do you see in T to G? Now find the CFSC value for me. 2 into 0.6 times delta naught minus 3 into 0.4 times delta naught. तो कितना हो गया ये टोटल? 0. Now come here. Find the CFSC for me over here. How many electrons are there in EG over here? But T to G. So this will be 0 into 0.6 delta naught minus 5 into 0.4 delta naught. Along with that, we also add something called as pairing energy. Notice pairing energy, since you're going against Hund's rule, that you're pairing them, which is not as per Hund's rule, a small amount of energy gets added to the actual energy, इसलिए we add that small amount. बाद में we'll also write थोड़ा सा theory to understand where exactly pairing takes place and where there is no pairing if you compare octahedral energy and pairing energy. So find this for me, कितना होता है ये? -2 delta naught plus. Now this energy is still less compared to the CFSC that we have here. And remember, lower the energy, higher is the stability. And that is why we need certain conditions, I'll tell you later. And only in these certain conditions there will be pairing, else there will be no pairing. Let's say we find the same for D6. How will D6 look like before pairing? Now how will D6 look like after pairing? Can someone quickly find the CFSC for me over here? Number of electrons in EG, 2. So how much will that be? 2 into 0.6 times delta naught minus 4 into 0.4 times delta naught. How much is that total? Minus 0.4 delta naught. Let's find CFSC for me over here. Number of electrons in EG, 0 minus number of electrons in T2G, 6 into 0.4 delta naught plus pairing energy. How much is that? And hence under certain conditions, when pairing takes place, it is more stable as compared to when there is no pairing. So D5 and D6 के लिए तो मैंने ढूंढ के निकाला है. You will find the CFSC for D7 and D4. इसके लिए आप लोग निकालना. Find CFSC before and after pairing. Now, if I give you D1, what will the CFSC be before pairing and after pairing? Will it be same? Yeah, different. So it's just D1. So what will the value be before pairing? EG is 0, T2G is 1. इसको pair करने के लिए getting that बोलो रे. Next, if I give you D2, before pairing, EG is how much? 0. T2G is 2. After pairing, इसको pair करेंगे क्या? No, it makes no sense. Why? Why are we pairing EG का T2G का electrons in? Pairing किसके बीच में होता है? When you move electrons from, यहाँ पे EG में electrons ही नहीं है. So D1 हो या D2. Next, what about D3? Same, because all the electrons are present in. What about D8? This is D8 before pairing. Will you pair EG का electron in EG? No. So for D8, D9 and in octahedral complexes, even in the presence of, ठीक है, अब तो ये पढ़ाया नहीं, but पढ़ाऊंगा, even in the presence of something called as a strong field ligand, no pairing takes place. Did you get that? So pairing कौन से configuration के लिए होता है? So you will look for configurations D, D, D and D. These configurations may pairing takes place only in the presence of a strong field ligand, SFL. Now what are strong field ligands? Except halogens and aqua or aquo, all ligands are so while doing VBT with modification of CFT, you will look for two rules. There are two steps that you have to properly check. First, you will check whether the central metal ka configuration is D4, D5, D6, D7. Then you will check whether the ligand is, how do you know whether ligand is SFL? Except halogens and water, all are strong field ligands. So if you look at the first example जो हमने किया था, Fe के साथ what was the ligand? Is water a strong field or a weak field? hence no pairing. What is the configuration of Fe over there? D6. But D6 with a weak field, will there be pairing? No. But when you come here, Fe, again the configuration is D6. What is cyanide? It's a strong field ligand. Whenever there is an SFL, you will perform pairing of the electrons. So how do you decide SFL and WFL? दो चीज़ें, एक तो मैं एक लिस्ट दूंगा, उसको मगअप करना है. But it is the property of donation of lone pairs which decides whether a ligand is strong field or weak field. Did you will get that? Yes or no? Sarthak. Right on. Find hybridization geometry and magnetic moment hybridization geometry and magnetic moment for the following complexes. Chalo. Now pay attention here, everyone. All you have to do is just remember the rules. Let's start with the first complex. Give me the first one, people. What's the first complex? CO Cl6 the whole raised to 4 minus. Okay. Now, quickly give me the charge on cobalt over here. So cobalt will be 2 plus cobalt. Electronic configuration 4s2 3d7. Yes or no? Pay attention, please. But what's the charge on cobalt over here? Plus 2. So what will now the configuration be for cobalt plus 2? 3d7. 4s 0. Now I have a question. Is Cl a strong field ligand or a weak field ligand?
Weak field.
Chlorine is a weak field ligand, and in case of weak field ligands, pairing takes place or no pairing? No pairing. तो क्या आ जाता है because of no pairing? 3d7 will be something like this. 3d7, 1, 2, 3, 4, 5, 6, 7. And where will I accommodate the electrons? 4s. How many electrons in 4s? 2. How many in 4p? How many lone pairs? 3. How many lone pairs in 4d? 2 lone pairs. Give me the hybridization, please. sp3d2. Where did these electrons come from? What is the geometry octahedral? And what is the bond? Sorry, a magnetic moment. How many unpaired electrons are there? So 3 into, so that is root. Such complexes where no pairing takes place are also called as high spin complexes. I repeat, what do we call them as? High spin complex. And they are also called as outer orbital complex. Did you get that? Outer orbital, because we are using the 4s, 4p and 4d of the metal. Now, give me the second one. Give me the second one. CO OX thrice, the whole raised to, what was OX? Which ligand was OX? And give me the denticity of OX. Go back and quickly check and tell me which ligand was OX and what was its denticity. Excellent. OX was a bidentate. Which bidentate was OX? Oxalato. And what is the charge on oxalato? So now quickly give me the charge on cobalt over here. The oxidation number on cobalt is +3. So cobalt configuration argon 3d7, उधर तो लिखा है 4s2. Now give me cobalt +3. How will cobalt +3 look like? There's going to be argon 3d6 4s. Now tell me, what will we check next? Oxalato is a strong field ligand. Since it's an SFL, what will happen? Pairing takes place. Samjha people? Bolo re. Since pairing takes place, how will 3d6 look like? The 6 electrons will be paired against Hund's rule. aa raha hai samajh mein? Yes or no? And now we have 4s and we have 4p. What are we going to do over here? Accommodate how many lone pairs? 6 kaise, but yahan pe 3 hai. So why are you saying 6 lone pairs? Because oxalato is a bidentate, which means each oxalato is going to give how many lone pairs? So 6 lone pairs. 1, 2, 3, 4, 5 and 6. Now give me the hybridization, please. Hi. Hybridization, please. The hybridization is D2sp3. Geometry remains magnetic moment. Wherever pairing takes place, such complexes are called as low spin complexes. It's very obvious. Spin sub pair ho gaya na. There is no spin. Low spin complex. And since the inner d orbital of the metal is used, these are called as inner orbital complexes. समझ में आ रहा है? बोलो रे. इवेंचुअली ये सब माइंड में करना है एग्जाम में, इतना लिखना नहीं है. गिव मी द नेक्स्ट वन. MnH2O6. Now everyone will pay attention here. We'll do this mind में. In MnH2O6 2 plus. What's the charge on Mn? 2 plus. What is the electronic configuration of Mn? 25 atomic number. Electronic configuration, please. 4s2 3d5. What will the configuration be for Mn plus 2? 3d5. 4 is 0. Now d5 is water a strong field ligand or a weak field? Will pairing take place? No. So what will the hybridization be? sp3d2. वो 4s4 पे 4d यूज होंगे. Number of unpaired 3d5 5 unpaired. Magnetic moment root of 5 into 5 plus 2 root 35. समझा? Is it diamagnetic or paramagnetic? There are unpaired electrons. Paramagnetic. समझ में आया? Is it a high spin complex or a low spin complex? High spin complex. Wherever there is no pairing. Is it an outer orbital complex or an inner orbital complex? Smart. Next. MnCN6 4 minus. Again, what's the charge on Mn? Charge on Mn? 2 plus. Electronic configuration 3d5 4 is 0. Same. But Cn is a strong field ligand and hence dash will take place. So what will now the configuration be? D2sp3. Why? Because वो 5 है, वो 2 shift हो जाएंगे. But there will still be one unpaired. वापस से D5. Remember D5 is getting paired. So 1, 2, 3, 4. Actually जब हम बनाएंगे तो उसको when you want to visualize उसको ऐसे visualize कर सकते हो. These two belonged to, they are going to, but लिखते टाइम हम ऐसा लिख सकते हो. But you will get that. बोलो ने. Next we have CrH2O. What is the complex? Give me. CrH2O6. The whole plus 3. Jaldi charge on chromium over here. Plus 3. Chromium electronic configuration 20, atomic number 24. Electronic configuration. Excellent. Half filled है ना वो. 3d5 4s1. So chromium plus 3 क्या हो जाएगा people? Excellent. 3d3. What is the configuration? D3. What is the configuration? What is the configuration? D3. If configuration is D3, कुछ मैटर करेगा क्या वेदर इट इज स्ट्रॉन्ग फील्ड और वीक फील्ड? समझ में आ रहा है? इट इज गोइंग टू रिमेन अनपेयर्ड, सेम ऐसा. Yes or no? So which orbital will you use? 4s and 1 in 4s and so what is the hybridization? D2. Is it a high spin complex or a low spin complex?
High spin.
They are unpaired. It's a high spin complex. But inner orbital or outer orbital? Why inner? We have used the D of the metal. इसलिए उसको हम क्या बोलेंगे? Inner orbital complex. Why is it a high spin complex? Presence of unpaired electrons. समझा कि नहीं समझा? बोलो रे. The last one which is left, वो हम next class करेंगे. हाँ. वो थोड़ा सा अलग है और अभी तक हमने exceptions चालू भी नहीं किया. इसका exceptions है बहुत सारे. When the d orbital of the metal is used, जब sp3d S से start, S भी पढ़ लो, S से start हो रहा है तो it is outer orbital complex. Inner orbital complex will always start from a D2. It is the inner d orbital of the metal which is being used. समझा people? ठीक है, we stop here for the day. ये जो FeCO5 है exception, ये छोटा सा अलग है and there are some list of exceptions जो हम next class लिखेंगे. Thank you.